Okay, so we can also look at other carbon molecules, charged molecules and radical molecules, and see the hybridization by determining the number of electron domains. So in this slide, if you read the title, the carbon and methyl cation and methyl radical are sp2 hybridized. And we can show that by counting the bond sites. So in methyl radical, carbon has 3 bonds and no lone pairs. When you have 3 bonds, that is 3 electron domains, and 3 electron domains is equivalent to sp2 hybridization. Now, carbon radical, the methyl radical shown at the bottom, also is sp2 hybridized because an electron domain is defined as the number of bond sites plus the number of electron pairs. Because the radical has only 1 electron and not an electron pair, it does not count as an electron domain. The only domains are the bonds, or the bond sites. So this carbon radical, methyl radical, has only 3 electron domains. And we can denote that by saying it has 3 electron domains, or 3 eds. They both have 3 eds, and therefore their geometry is sp2. And sp2 geometry has a molecular geometry of trigonal planar. The carbonated methyl anion is sp3 hybridized because we have 4 electron domains, 3 bonds and 1 lone pair. 3 bond sites, 1 lone pair, LP, equals 4 eds equals sp3. Now in this case, the molecular geometry for 3 bond sites and 1 lone pair is trigonal pyramidal. If you don't remember your molecular geometries, you need to open up your Gen Chem book and review them. I'll say them here without writing them down for a reminder. If you have no lone pairs and only bond sites, you have 1 bond site, that is a linear geometry. If you have 2 bond sites and no lone pairs, that is still linear geometry. If you have 3 bond sites and no lone pairs, that is trigonal planar geometry. If you have 4 bond sites and no lone pairs, that is tetrahedral geometry. Geometry gets confusing only when we start to add lone pairs. So when there are no lone pairs, the number of bond sites equals the number of electron domains is equal to molecular geometry and electron domain geometry. But what about the other molecular geometries? Some of the ones that you might remember are trigonal pyramidal, bent for water. What else? There's square planar and trigonal bipyramidal and seesaw and etc. Now those geometries that involve exceeding an octet are not going to be covered in this class. So we're not going to worry about octahedral, trigonal bipyramidal, seesaw, square planar, or any of the upper level exceeding an octet geometries. But for those that don't exceed an octet, the ones which have lone pairs is that if you're like water and you have 2 bonds and 2 lone pairs, then you are bent. If you're like ammonia and you have 3 bonds and 1 lone pair, then you have trigonal pyramidal geometry. So ammonia, nitrogen has 5 valence electrons. 3 electrons for an octet forms 3 bonds. 5 plus 3 is 8. Or it needs 3 more electrons to form an octet. So it's only going to form 3 bonds, and the number of bonds formed plus the number of valence electrons should add to 8. Nitrogen is going to has 3 bond sites and 1 lone pair, and so the nitrogen in this is sp3 hybridized. And the geometry is trigonal pyramidal. Three bond sites and 1 lone pair, trigonal pyramidal. The bond sites in ammonia are formed with sp3 hybridized orbitals, and so the nitrogen to hydrogen bonds are sp3 to s orbitals, and the lone pair of nitrogen rests in an sp3 orbital. So you should remember that the lone pair of nitrogen is also in an sp3 orbital. Notice that the ball and stick formula representing the three-dimensional shape, and then the electrostatic potential map showing the distribution of electrons focused in the lone pair. The ammonium ion, when nitrogen forms 4 bonds and it has 4 electron domains because of the 4 bond sites, it's going to have a positive charge. It's still sp3 hybridized, but now the molecular geometry is tetrahedral because there are no lone pairs. And so the bond angles will be 109.5. And notice the electrostatic potential map showing very low electron density overall due to the positive charge and reflecting the positive charge with the blue color. Water has 6 valence electrons. It needs 2 more electrons to form an octet and therefore makes 2 bonds. That means that it has 2 bond sites and 2 lone pairs. That would be bent geometry. It's sp3 hybridized. It has 2 bonds and 2 lone pairs, and the geometry is what we call bent. The lone pairs rest in sp3 orbitals, and the sigma bonds are sp3 to s overlap, sigma bonds. Bonding of halogens is forms a linear molecule, and the halide is sp3 hybridized. The halogen has 7 valence electrons, and it needs 1 electron for an octet. So it forms 1 bond. The halogen uses hybrid orbitals. It has a molecular geometry of linear. If you draw out the Lewis structure, including electrons for hydrogen fluoride, you should have 6 dots, which gives us 1 bond site and 3 lone pairs. That is still 4 electron domains, and so it is sp3 hybridized. This is what we called earlier a polar bond because of the large difference in electronegativity between fluorine and hydrogen. The difference is about 1.9, that is 4 to 2.1, for the electronegativity values, or 2.2. And remember, electronegativity can be symbolized using En. Therefore, the difference in electronegativity is 1.8. And an electronegative difference of 1.8 is defined as a polar bond, polar covalent bond. The overlap of an s orbital with an sp3 orbital for hydrogen versus the sp3 orbital of fluorine, chlorine, bromine, and iodine is going to be different. The more similar the orbitals are in size, the greater the region of overlap. As one orbital becomes excessively bigger than the other, the region of overlap becomes smaller and the bond becomes weaker. And this should match the periodic trends that you learned last year, where bond strength decreases as you go down a group. So that HF with hydrogen and fluorine in the same row having roughly the same molecular orbital size is a very strong bond, while the sp3 orbitals of chlorine, bromine, and iodine get larger as you go down the group. The overlap to that s orbital of row 1 decreases and the bond strength decreases. Length and strength of a hydrogen halide bond is described in this table. It's showing you the length and the strength. So as you go down a group on the periodic table, you should remember that bonds get longer and weaker. So that when you're with have hydrogen halide, the bond length is less than 1 angstrom, and an angstrom is 1 times 10 to the negative 10th meters, and the bond strength is 136 kilocals per mole. When we go down to hydrogen halide, the bond length is 1.609, a little bit less than twice as long as the HF bond, and the strength is almost half that of the HF bond at 71. Hybridization and molecular geometry are important. An sp3 hybridized orbital could be tetrahedral, linear, or bent, depending on the number of lone pairs. In ethane, shown above, it is sp3 hybridized and the geometry is tetrahedral. The middle molecule is sp2 hybridized and trigonal planar, and the final molecule is sp hybridized and linear. But you should remember that you do need to know your molecular geometries. You do need to know what are the characteristics of bent geometry and trigonal pyramidal geometry. You don't have to know the bond angles specific to those geometries. We will just use a general bond angle. For all sp3 hybridized, we'll say they're 109.5, for all sp2 120, and for sp hybridized 180. Single bonds are sigma bonds, double bonds are 1 sigma bond plus 1 pi bond, and triple bonds are 1 sigma bond plus 2 pi bonds. And this is something that you should have learned in Gen Chem, but that you need to memorize now. Multiple bonds contain 1 sigma bond, and all other bonds of a multiple bond are pi bonds. So a single bond is always a sigma bond. A pi bond is always 1 sigma bond, and a double bond is always consists of 1 sigma bond and 1 pi bond, and a triple bond always consists of 1 sigma bond and 2 pi bonds. And you should also note that double bonds almost always are going to result in sp2 hybridization, and triple bonds in sp hybridization. You can, if you need to do the work, then you can simply count the electron domains, which in this case would be the bond sites, to determine the hybridization of each atom. Here's an exercise in practice. I will show you what we're going to do.